A robot just did a backflip. Think about that. A hunk of metal did a backflip. Your cousin can't do a backflip. Your cousin has a spine, muscles, and 22 years of practice. The robot has aluminum and math. The robot wins. Okay, but here's the thing. That backflip didn't just happen. Nobody programmed do backflip into a robot and it worked. What actually happened is one of the most insane engineering stories in human history, and it involves calculus, motors the size of your fist, and engineers literally hitting robots with golf clubs to see if they fall over. This is robotics, and it goes way deeper than you think. Let's start at the beginning. Not the robots in sci-fi beginning. The actual beginning. The real question underneath all of robotics is almost embarrassingly simple. How do you get a piece of metal to move to a specific place? And that's it. That's the whole game. Everything else, the backflips, the robot arms in car factories, the little Roomba your cat is riding right now, all of it is just a more complicated version of that one question. Move this thing to that place. Accurately. Repeatedly. Without destroying everything around it. So why is that hard? Huh? You've moved your arm to a specific place 1,000,000 times today. You grabbed your phone. You opened a door. You didn't think about it. Your brain just did it. But here's what your brain actually solved without telling you. What? It took the position of an object in 3D space, figured out the exact angle every joint in your arm needed to be at, fired the exact right muscles in the exact right sequence, and adjusted in real time when it was slightly off, in about 50 milliseconds. Your arm is doing insane math. All the time. Without you knowing. That's what robotics is trying to copy. So let's talk about the first piece of this puzzle, kinematics. Don't let that word scare you. Kinematics is just the study of motion. Not why things move, that's dynamics, that comes later, just how they move. Where does a joint end up if you rotate it this many degrees? How does moving one part of an arm affect where the tip of the arm ends up? Simple question. Wildly complicated answer. Imagine a robot arm with two joints. Like your elbow and your shoulder. If you rotate your shoulder 45 degrees and your elbow 30 degrees, where's your hand? You could try to calculate that with geometry. And you'd be right. But now add a wrist. And a wrist that can rotate, and a second wrist that tilts. And suddenly, you have 6 joints all stacked on each other, each one depending on the angle of the previous one, and you need to figure out exactly where the tip of that arm ends up in 3-dimensional space. This is called forward kinematics. And the math for it involves something called transformation matrices, which is basically a set of equations that says, if I'm sitting at this angle and this position in space, here's how to translate a point from my perspective to the world's perspective. Every joint is a new matrix. Every joint adds a new layer of complexity. Chain 6 of them together, and you've got a system that would take a page of math just to describe the arm moved 3 inches to the left. But here's where it gets actually wild. Forward kinematics, going from joint angles to position in space, is hard. The reverse of that, N. Going from a desired position in space back to the joint angles needed to get there, N. That's called inverse kinematics, and it is a completely different level of brutal. Sometimes there are multiple solutions. Sometimes there are infinite solutions. Sometimes there are none. Your robot arm needs to reach a point, and the math gives you back 3 different ways to get there, and no obvious reason to pick one over the others. And that's just for position. You haven't even started worrying about orientation yet. The arm can be in the right place, but pointing the wrong way. And now you have to solve for both at once. This is the stuff that makes robotics engineers cry into their coffee at midnight. But also, and this is important, this is what makes it beautiful. Because solving this problem is what lets a robot arm in a factory weld the exact same point on a car frame 2,000 times in a row within a millimeter of precision. Every single time. That's not just engineering. That's poetry written in linear algebra. But wait, we haven't even put motors in this arm yet. We haven't talked about how it actually moves. And that's where things get really interesting. Okay, so we know the math that says rotate joint 2 by 37.4 degrees, and the robot's hand ends up exactly where we need it. Great. Love that. Now how do we actually rotate joint 2 by exactly 37.4 degrees? You can't just say, motor, go. You try that, the motor goes too far or not far enough, your robot punches a wall, and everyone looks bad. This is where actuators come in. And actuators are doing way more work than they get credit for. An actuator is anything that creates physical motion in response to a signal. Electric motors are the most common kind in robotics, and there are a few types you need to know. The workhorse is the DC motor. Give it voltage, it spins, more voltage means more speed, flip the polarity and it spins the other direction. Simple. Beautiful. But it spins is not the same as it goes exactly to this angle. For that, you use a servo motor, which has a built-in position sensor and a small internal control system that says I should be at 37.4 degrees, I'm at 34 degrees, let me fix that. Servo motors are why robot arms can hold a position without shaking. They're arguing with themselves thousands of times per second to stay still. Then there's the brushless DC motor, which is what you find in anything that needs to be fast, powerful, and efficient. Drones, high-performance robot joints, basically anything where you can feel the engineering budget in your hands. And for really heavy-duty stuff, there are hydraulic actuators, controlled by pressurized fluid, which is what gives those giant industrial robots the ability to lift a car like it's nothing. Your average electric motor in a robot arm isn't picking up a car. Hydraulics can. But here's the thing about all of these. None of them are perfect. Every motor has error, mechanical play, friction, tiny imprecisions in manufacturing. You tell a motor to go to 37.4 degrees and it goes to 37.6. No big deal for picking up a coffee cup. Catastrophic if you're assembling a microchip or doing surgery. And this problem, the gap between where you told the system to go and where it actually went, is one of the central problems of all of robotics. It has a name. It's called error, and eliminating it is basically the entire job of control theory. Now here's where we hit the midpoint, and I need you to actually stop for a second. Because what I'm about to tell you is one of those things that sounds simple, but is secretly one of the most profound ideas in all of engineering. Wow. Every system in the universe that does something and then gets feedback about how it did and then uses that feedback to do the next thing better is called a closed loop system. Your body is a closed loop system. Your eyesight and your hand are in constant dialogue. You reach for a glass, your eyes tell your brain where your hand is versus where the glass is. Your brain corrects your arm trajectory. You grab the glass. You didn't think about any of that. But strip away the biology, and that's just a feedback loop. Sense, compare, correct. Sense, compare, correct. Over and over at insane speed. Robotics copied this. Completely. The version they use is called a PID controller. Proportional integral derivative. Sounds terrifying. Is actually beautiful. Here's what it does. It takes the error, the difference between where you are and where you want to be, and computes a correction signal using 3 terms. The P term says, the bigger the error, the harder you push to fix it. The I term says, if you've been slightly wrong for a long time, accumulate that wrongness and correct for it. The D term says, if you're correcting fast, slow down so you don't overshoot. Put those 3 together, and you have a system that zooms toward a target, doesn't blow past it, and settles in exactly where you want it, even when external forces are messing with it. And when you tune a PID controller badly, the robot oscillates. It wiggles around the target value forever, overcorrecting, undercorrecting, overcorrecting again. It looks like a robot having a very small, very precise panic attack. And this, by the way, is why engineers spend entire weeks just tuning PID parameters. Too much P and the system overshoots violently. Too little D and it never settles. It's weirdly similar to adjusting how hard you try in a relationship. Too eager, and you overshoot. Too passive, and you never reach the goal. Anyway, PID controllers are everywhere. In your car's cruise control. In the thermostat in your house. In insulin pumps. In airplane autopilots. In the gimbal that keeps your phone camera smooth when you're running. Once you know what a PID controller is, you start seeing them literally everywhere. And you realize that one elegant idea from the 1920s is secretly running a huge chunk of civilization. But here's the thing about a PID controller. It's great at keeping one thing stable. What happens when you have a robot with 6 joints, all moving at once, all affecting each other, all needing to stay on target simultaneously, and the whole robot is also trying to walk? Because now we're not talking about a robot arm bolted to a factory floor. Now we're talking about a robot that has legs. And legs introduce something that a stationary arm never has to deal with. Falling. A legged robot is, at every single moment, a system in the process of falling that keeps catching itself. That's not a metaphor. That's the actual physics. When you walk, you fall forward and catch yourself with your next step. Every step you take is a controlled fall. Your brain handles the catching part so automatically that you've completely forgotten it's happening. A robotics engineer cannot forget it. They have to explicitly code it. They have to understand it deeply enough to write it down in math. This is where sensors become everything, because a robot that doesn't know it's falling can't catch itself. So, modern legged robots are covered in sensors the way your nervous system is covered in nerve endings. They have IMUs, inertial measurement units, that measure acceleration and rotation in all 3 axes, telling the robot exactly how it's tilting and how fast. They have force sensors in their feet that measure how hard the ground is pushing back. They have encoders on every joint that track position and velocity. They have cameras and LiDAR for seeing the world around them. The robot doesn't just move. The robot is constantly reading the world and reading itself, and comparing the 2 hundreds of times per second. And all of that sensor data feeds back into the control system, which is no longer just a PID controller, it's a whole stack of controllers at different levels, each handling a different job. One layer handles individual joint angles. Another layer handles the position and orientation of the whole body. Another layer plans which foot goes where and when. And above that, maybe, is a higher level planner that decides where in the room the robot is going and how to get there without walking into a wall. This architecture is called hierarchical control, and it's basically how your own brain works. Your spinal cord handles the reflexes, your cerebellum handles balance, your motor cortex handles intentional movement, your prefrontal cortex handles planning. Robotics didn't invent this idea. Robotics discovered that nature already solved it, and then slowly, painstakingly copied it in metal. Now, about those engineers hitting robots with golf clubs. This is a real thing. Boston Dynamics engineers are famously documented in videos pushing, kicking, and smacking their robots to test robustness. And the robots stay up. Get shoved sideways, stumble, recover, keep walking. This isn't cruelty. This is testing. The robot's control system has to handle not just nominal conditions, but every chaotic, unpredictable thing the real world can throw at it. Slippery floors, uneven terrain, someone messing with it. The gap between a robot that works in a lab and a robot that works in the real world is basically the gap between conditions I designed for and conditions I didn't. Closing that gap is one of the core open problems in robotics. Which brings us back to the backflip. When Boston Dynamics' Atlas robot does a backflip, what is actually happening is this. A pre-computed motion plan generated by optimization algorithms that search through millions of possible trajectories is being executed at high speed, with onboard sensors correcting in real time for any deviation between what the plan said would happen and what's actually happening. The robot doesn't know it's doing a backflip the way you know it. It's executing a very precise, very fast sequence of joint torques, monitored and corrected at every millisecond. The whole thing is over in about a second. If the correction loop fails for even a fraction of that time, the robot falls on its face. And it has. Many times. The blooper reel is incredible. But zoom out. Look at where we started. We started with, how do you get a piece of metal to move to a specific place? We went through the math of joint angles, the mechanics of motors, the elegance of feedback control, the insanity of legged locomotion. And now we're watching a 100-kilogram machine do gymnastics. That arc, from theory to backflip, is one of the genuine triumphs of human engineering in the last 50 years. Here's your awe moment, and I want you to sit with it. Wah! The control algorithms running in modern robots are not programmed by human engineers anymore. The most advanced ones are learned. Researchers create a simulated environment, put a virtual robot in it, and let it try to walk, failing millions of times until it discovers, on its own, a strategy that works. Then they transfer that learned behavior to the real robot. The robot didn't read a textbook. It didn't have physics explained to it. It failed its way to competence. Sound familiar? Yeah. It learned the way you learn to walk. And nobody fully understands why the strategies it discovers work as well as they do. The math that describes what the robot learned is too complex for a human to read. So here's the question that nobody has answered yet. We've built machines that can outrun us, outlift us, outprecise us. We've given them the ability to learn motor skills from scratch. We've watched them recover from falls in ways that look genuinely like instinct. At what point does a machine that senses its environment, models itself, learns from failure, and adapts in real time stop being a very complicated calculator and become something else? We don't have a clean answer to that. And the fact that we don't is maybe the most interesting thing about this entire field. The metal is getting smarter. We're the ones who built it that way. And the golf clubs? Probably weren't a great idea in retrospect.